The microarchitecture of a superscalar processor. Abstract. The superscalar programming processing is the latest long series of innovations aimed at producing the ever-faster microprocessors by exploring the instruction-level parallelism. Superscalar processors are capable of executing more than one instructions in a cycle. This paper discusses the microarchitecture of superscalar processors. We begin with the discussion of the general problem solved the superscalar processor, converting an ostensible sequential program into a more parallel one. The principles underlying this process, the constraints that must be met, are discussed. The paper that provides a description of a specific implementation techniques used in the important phases of the superscalar processing. The major phases include instruction fetching, conditional branching processing, the determination of the data dependencies involving register values. 3. The initiation or issuing of the instruction for parallel execution. 4. The communication of the data values through the memory via load or stores. 5 is committing the process state in correct ordering so that the precise interrupt can be supported. So examples of the recent superscalar microprocessor, the MIPS R10000 and DEC 21164 and the AMD K5 are used to illustrate the variety of scalars method. 1. Introduction. Chapter 1. The superscalar processing, the ability to initialize multiple instructions during the same cycle, so the latest is in a long series of architectural innovation aimed at producing an ever-faster microprocessor introduced at the beginnings of this decade. Superscalar microprocessors are now being designed and produced by all the microprocessor vendors for a high-end product. Although viewed by the many of the extension of the reduced instruction set computer RISC movement of the 1980s. Superscalar implementations are in fact heading toward increasing complexity, and a superscalar method have been applied to a spectrum of the instruction sets ranging from the DEC alpha, the newest RISC instruction set, to the decidedly non-RISC Intel x86 instruction set. So, a typical superscalar processor fetches and decodes the incoming instruction stream several instructions at a time. As a part of the instruction fetching process, the outcome of the conditional branch instructions are usually predicted in advance to ensure that an uninterrupted stream of instructions. The incoming instruction streaming is then analyzed for data dependencies, and the instructions are distributed to the functional unit, so often according to the instruction type. Next, instructions are initiated for execution in parallel based primarily on availability of the operand data, is referred to as dynamic instruction scheduling. So upon completion, the instructions results are sequenced so that they can be used to update the process state in correct original program order in event that an interrupt condition occurs. Because individual instructions are entities being executed in parallel, superscalar processors exploit what is referred to as instruction-level parallelism (ILP). Section 1.1 as an historical perspective. The instruction-level parallelism in form of the pipelining has been around for decades. So a pipeline acts like an assembly line with instructions being processed in phases as they pass down the pipeline. With a simple pipelining, only one instruction at a time is initiated in the pipeline, but multiple instructions may be some phase of execution concurrently. Pipelining was initially developed in the late 1950s and becoming a mainstay of a large-scale computer during the 1890s. So the CDC 6600 used a degree of pipelining, but achieved the most of each ILP through the parallel function instruction set as functional unit. So although it was capable of the sustained execution of only a single instruction per cycle, the 6600 instruction set. The parallel processing unit and dynamic instruction schedulings are similar to a superscalar microprocessors of the day. Another remarkable processor of the 8090s was the IBM 36091, and the 36091 was the heavily pipeline that provided a dynamic instruction using the mechanism known as a Tomasulo algorithms. As after each inventor, as with the CD 6600 and the IBM 306091 could sustain only one instruction per cycle, was not superscalar. But the strong influence of the Tomasulo's algorithms is evident in many of today's superscalar processors. So the pipeline initiators rate remained at one instruction per cycle for many years and was often perceived to be a serious practical bottleneck. Meanwhile, the other avenues for improving the performance via parallelism were developed, such as vector processing and multiprocessing, although some processors capable of multiple instruction initiation were considered during the 60s and 70s. None were delivered to a market. Then, in the middle of the late 1980s, superscalar processors began to appear. By initiating more than one instruction at a time into multiple pipelines, superscalar processors break the instruction set in single instruction per cycle bottleneck. In the years since its introduction, each superscalar approach has become the standard method for implementing high-performance microprocessors. Chapter 1.2, the Instruction Processing Model. Because the hardware and software involved, it is rare for a processor architect to start with a clean slate. Most processors designed inherit a legacy from their predecessors. The modern superscalar processors are not different. A major component of this legacy is binary compatibility, the ability to execute a machine program written for an earlier generation processor. So when the very first computers was developed, each had its own instruction set for reflected specific hardware constraint and design decisions at the time of instruction set development. Then the software was developed for each instruction set, so it did not take long, however, until it became apparent that there was a significant advantage to designing instruction sets that were compatible with the previous generations with the different modules of the same generation. For a number of practical reasons, the instruction set architecture or binary machine language level was chosen as the level of maintaining the software compatibility. The sequencing model inherent in instruction sets and program binaries, the sequential execution model closely resembled the way processors were implemented many years ago. So in sequential execution model, a program counter is used to fetch a single instruction from memory. The instruction is then executed, and the processor may load or store data to memory or operate on registers held in the processor. Upon completing the execution of the instruction, the processor uses an incremented program counter to fetch the next instruction, with the sequential instruction processing occasionally being directed by a conditional branch or a jump. Should the execution of the program needed to be interrupted and restarted later, for example, in case of the page fault or other exception condition, the state of the machine needs to be captured. The sequential execution model has led naturally to the concept of a precise state. At the time of the interrupt, the precise state of the machine, architecturally visual registers and memory, is the state that would be present if a sequential execution model was strictly followed and processing was stopped precisely at the interrupted instruction, Restart could then be implemented by simply resuming the instruction processing with the interrupted instruction. Today, a computer designer is usually faced with maintaining binary compatibility, that is, maintaining instruction set compatibility and the sequential execution model, which typically implies precise interrupt. For high performance, however, the Superscalar processor implementations deviated radically from sequential execution. Much has to be done in parallel. As a result, the program binary nowadays should be viewed as a specification of what has to be done, not how it's done in reality. A modern superscalar microprocessor takes the sequential specification as embodied in the memory binary, a program binary, and removes much of the non-essential sequentiality to turn the program into parallel. The higher performance version, and yet the processor retains the on-world appearance of a sequential execution. 1.3 Elements of high performance processing. Simply stated, achieving the higher performance means processing a given program in a smaller amount of time. Each individual instruction takes some time to fetch and execute. This time is the instruction latency. To reduce the time to execute a sequence of instructions, for example a program, one can reduce the individual instruction latencies or to execute more instructions in parallel. Because of the superscalar processor implementation, they distinguished by the latter, while the adequate attention is also paid to the former. We will concentrate on the latter method on this paper. Nevertheless, a significant challenge in a superscalar design is to not increase the instruction latencies due to the increased hardware complexity brought about by the drive for enhanced parallelism. The parallel instruction processing requires the determination of the dependency relationship between the instructions, adequate hardware resources to execute multiple operations in parallel, strategies determine when an operation is ready for execution, and techniques to pass the values from the one operation to another. When the effect of the instructions are committed, and the visual state of the state machine updated, and the appearance of the sequential execution must be maintained. More precisely, in hardware terms, this means a superscalar processor implement the one faster instruction fetch strategies that are simultaneously fetch multiple instructions, often by predicting the outcomes of and fetching beyond conditional branch instructions. 2. The method for determining true dependencies involves register values and mechanisms for communicating these values to where they are needed during execution. 3. Method for initiating and issuing multiple instructions in parallel. 4. Resources for parallel execution of the many instructions, including the multiple pipeline functional unit and memory hierarchies capable of simultaneously servicing the multiple memory references. 4. Method for communicating data values through the memory via load and store instructions and memory interfaces that allow the follow dynamic and often unpredictable performance behavior of the memory hierarchies. These interfaces must be well matched with the instruction execution strategies. 6. Method for committing the process state in correct order. These mechanisms maintain an outward appearance of the sequential execution. So although we will discuss the above items separately, in reality they cannot be completely separated, nor should they be. In good superscalar designs, they are often integrated in cohesive, almost seamless manner. 1.4 The paper overview. In section 2, we discussed the general problems solved by a superscalar processor converting an ostensibly sequential program into a parallel one. This followed by a section 3 with a description of specific techniques used in typical superscalar microprocessors. Section 4 focuses on 3 recent superscalar processors that illustrate the spectrum of the current techniques. Section 5 is present a conclusion and discusses future directions for an instruction-level parallelism. 2. Program representations, dependencies, and parallel execution. The on-application begins as a high-level language program. It is then compiled into a static machine-level program or the program binary. The static program, in essence, describes a set of executions, each corresponding to a particular set of data is given to the program. Implicit in the static program is sequencing model. The order in which the instructions are to be executed. So figure 1 shows the assembly code for a high-level language program fragment. The assembly code in the human-readable version of the machine code. We will use this code fragment as a working example. As a static program executes with a specific set of the input data, the sequence of executed instructions forms a dynamic instruction stream. As long as the instructions to be executed are consecutive and static instructions can be entered into dynamic sequence simply by incrementing the program counter, which points to the next instructions to be executed. When there is a conditional branch or jump, however, the program counter may be updated to a non-consecutive address. An instruction is said to be the controller dependent on its preceding dynamic instructions because of the flow of control program. A program controller must pass through preceding the instruction first. The two methods of modifying the program counter, incrementing and updating. The result in two types of control dependencies, though typically when people talk about control dependencies, so that they tend to be ignored the former. The first step, the increasing the instruction set parallelism, is to overcome the control dependencies. Control dependencies to do the unincrementing program counter are the simplest, and we deal with them first. One can view the static program as a collection of basic blocks, where a basic block is a contiguous block of the instructions with a single entry point and a single exit point. In the assembly code of figure 1, there are 3 basic blocks. The first basic block consists of the 5 instructions between the label 2 and an able BLE instruction, inclusive. The second basic block consists of 5 instructions between the BLE instruction, exclusive. And the label L3, and the third basic block consists of the 3 instructions between the label 3 and the BLT instruction, inclusive. So, once a basic block has been entered by the instruction fetcher, it's known that all the instructions in the basic block will be executed eventually. Therefore, any sequence of instructions in a basic block can be initiated into a conceptual window of execution en masse. We consider the window of instruction execution in a basic block can be initiated into conceptual window of execution. We consider the window of execution to be felt to be the full set of the instructions that may be simultaneously considered for parallel execution. Once instructions have been initiated into this window of execution, they are free to execute in parallel, subject only to data dependence constraint, which we will discuss shortly. Within the individual basic blocks, there is some parallelism, but to go more parallelism, control dependencies due to the update of the program counter, especially due to the conditional branches, have to be overcome. A method for doing this is to predict the outcome of the conditional branch and speculatively patch and execution instructions from the predicted path. Instructions from the predicted path are entered into windows of execution, so that if the prediction is later found to be correct, the speculative status of instructions is removed, and their effect of the state is the same as any other instructions. If the instruction prediction is later found to be incorrect, the speculative execution was incorrect, and this recover action must be initiated so that the architectural process state is not correctly modified. So we will discuss the branch instructions and the speculative execution more in detail in section 3. In our example, in figure 1, the branch instructions PLE creates a control dependence. To overcome this dependence, the branch could be predicted as not taken, for example, with the instructions between the branch and the label L3 being executed speculative. And the instructions that have been placed in the windows of the execution may begin execution subject to data dependencies constraint. Data dependencies occur among instructions because the instructions may access, read, or write the same storage as a register or memory location. When instructions references the same location, a hazard is said to be exist. That is, there is a possibility to incorrect operation unless some steps are taken to make sure the storage location is accessed in correct order. Ideally, the instructions can be executed subject only to true dependency constraint. These true dependencies appear as a read after write RAW hazard because the consuming the instructions can only read the values after the producing the instructions has written it. It's also possible to have artificial dependencies, and in process of executing a program, these artificial dependencies have to be overcome to increase the available level of parallelism. These artificial dependencies result from the write after read WAR and the write after write WAW hazard. A WAR hazard occurs when an instruction needs to write a new value into storage location, but must wait until all preceding instructions needing to read the old values have done so. And a AWA hazard occurs when multi-instructions update the same storage location and must appear that these updates occurs in proper sequence. Artificial dependencies can be caused in a number of ways, for example, by unoptimized code, by limited register storage, by the desire to economize on main memory storage, and by loops where instruction can cause a hazard with itself. Figure 2 shows some of the data hazards that are present in a segment of our working example. The move instructions produces a value in register R3 that is used for both the first LW and first LW and add instructions. This is the RAW hazard because the true dependency is present. The add instruction also creates a value which is bound to register R3. Accordingly, there is a WAW hazard involving a move and add instructions. A dynamic execution must ensure the access to R3 made by instructions that occur after the add in program access the value bound to R3 by the add instructions and not the move instructions. Likewise, there is a WAR hazard involving the first LW and the add instructions. Execution must ensure the value of the R3 used in the LW instruction is the value created by the move instruction, and not value created by the add instruction. After resolving the control dependence and artificial dependencies instruction, the RC are issued and begin the execution in parallel. In essence, the hardware forms a parallel execution schedule. This schedule takes into account necessary constraints, such as true dependencies and hardware resources constraint of the functional units and data paths. A parallel execution schedule often means that instructions complete execution in an order different from that dedicated by the sequencer execution model. Moreover, the speculative execution means that some instructions may complete the execution when they would not have executed at or had a sequential model been followed. That is, when speculative instructions follow an incorrectly predicted branch. Consequently, the architectural storage, the storage that are outward visible, cannot be updated immediately when instruction complete execution. Rather, the result of an instruction must be held in temporary status until the architectural state can be updated. Meanwhile, to maintain the high performance, this result must be usable by dependent instructions. Eventually, when it is determined that a sequential model would have been executed on instruction, its temporary results are made permanent by updating the architectural state. This is typically called committing and retiring the instructions. To summarize and to set the stage of the next section, Figure 3 illustrates the parallel execution method used in most superscalar processors. Instructions begin in a static program. The instruction fetch process, including branch prediction, is used to form a stream of dynamic instructions. These instructions are inspected for dependency with many artificial dependencies being removed. So the instructions are dispatched into windows of the execution. So in figure 3, the instructions within the window of the execution are no longer presented in a sequential order, but are partially ordered by their true data dependencies. Instructions issues from the window in order determined by the true data dependency and the hardware sources availability. Finally, after execution, the instructions are conceptually put back into sequential program order as they are retired and their result update architected process state. Chapter 3, the microarchitecture of the typical superscalar processor. Figure 4 illustrated the microarchitecture or hardware organizations of the typical superscalar processor. The major parts of the microarchitecture are instruction fetch, branch prediction, decode and register dependencies analysis, issue and execution, and memory operation analysis and execution, instruction reorder, and commit. These phases are listed more or less in the same order as the instructions flow through them. They will each be discussed in following subsections. Keep in mind that underlying the organization there is a pipeline implementation where the specific pipeline stage or may not be aligned with the major phase of the superscalar execution. The underlying the pipeline stage are to extend a lower level of the logic design issue. So depending on how much work is done on each pipeline stage, this affected the clock period and causes some important design trade-off regarding the degree of a pipeline and width of the parallel instruction issue. However, we will not discuss these issues in detail here. Discussions of these types of the trade-offs can be found in 13, 34, and 38. Figure 3, conceptual figure of the superscalar execution. Processing the phases listed across the top of this figure. The figure 4 is organization of the superscalar processor. And 3.1, section 3.1, instruction fetching and branch prediction. The instruction fetch phase of the superscalar processing supplies instructions to the last task of the processing pipeline. On instruction cache, which is a small memory containing recently used instructions, is used in almost all current processors, superscalar or not, to reduce the latency and increase the bandwidth of the instruction fetch process. An instruction cache is organized into blocks or lines containing several consecutive instructions. The Boolean counter is used to search the cache content associatively to determine if the instruction being addressed is present in one of the cache lines. If so, there is a cache hit. If not, there is a miss and the line containing the instruction is brought in from memory to be placed in the cache. For superscalar implementation to sustain the execution of the multiple instructions per cycle, the fetch phase must be able to fetch multiple instructions per cycle from the cache memory. To support the high instruction fetch bandwidth, it has become almost mandatory to separate the instructions cache from the data cache, although the PowerPC 601 provides an interesting counterexample. The number of instructions fetched per cycle should be at least match the peak instruction decode and execution rate and is usually somewhat higher. The extra margin of instruction fetch bandwidth allowed for instruction cache misses for a situation where fewer than a maximum number of instructions can be fetched. For example, if a branch instruction transfers control to an instruction in the middle of the cache line, then only remaining portion of the cache line contains useful instructions. Some of the superscalar processors have taken special steps to allow wider fetches in this case. For example, by fetching from two adjacent cache lines simultaneously, so as a discussion of a number of alternatives for high bandwidth instructions fetching appears in 11. To help smooth out the fetching, the instruction fetch irregularities caused by the cache misses and branches, there is often an instruction buffer shown in figure 4 to hold a number of fetches instructions. Using this buffer, the fetch mechanism can build up a stockpile to carry the processor through the periods when instruction fetching is stalled or restricted. The default instruction fetch method is incremental. The program counters the number of instruction fetches and use the incremented program counter to fetch the next block of instruction. In the case of branch instructions which redirect the flow of control, however, the fetch mechanism must be redirected to the fetch instructions from the branch target. Because of the delays that can occur during the process of this redirection, the handling of the branch instructions is critical to a good performance in superscalar processors. Processing of conditional branch instructions can be broken down into the following parts. 1. Recognizing that an instruction is a conditional branch. 2. To determine the branch outcome, taken or not taken. 3. Computing the branch target. 4. Transferring the control by redirecting the instruction fetching. In the case of the taken branch, the specific techniques are useful for handling each of the above. Recognizing the conditional branches. 2. This seems too obvious to mention, but it is the first step forward the fast branching processing. The identifying all instruction types, not just branches, can be sped up if some instruction decoded information is held in instruction cache along with the instructions. These extra bits allow the very simple logic to identify the basic instruction type. Consequently, there is often pre-decoded logic prior to the instruction cache. See Figure 4, which generates pre-coded bits and stores them alongside the instructions so they can be placed in the instruction cache. Next is to determine the branch outcome. Often when a branch instruction is fetched, the data upon which branch decision must be made is not yet available. That is, there is a dependence between the branch instruction to preceding uncompleted instructions. Rather than wait, and the outcomes of conditional branch can be predicted using one of the several types of the branch prediction method. Some predictors use static information, that is, information that can be determined from the static binary, either explicitly present or put there by the compiler. For example, the certain OP code types of the might more often result in taken branches than others, or the backward branch direction. For example, when forming loops, might be more often taken, or the compiler might be able to set a flag on an instruction to indicate the most likely branch direction based on the knowledge of the hardware higher-level language program. Profiling information, program execution statistics collected during a previous run of the program. can also be used by the compiler as an aid for static branch prediction. Other predictors use dynamic information, that is, information that becomes available as the program executes. This is usually information regarding the past history of branch outcomes, either the specific branch being the predicted, or the branches leading up to it, or both. This branch history is saved in a branch history table or a branch prediction table, or may be appended to the instruction cache line that contains the branch. The branch prediction table is typically organized in a cache-like manner and is accessed by the address of the branch instruction to be predicted. Within the table, previous branch history is often recorded by using multiple bits, typically implemented as a small counter so that the results of several past branch execution can be summarized. The counters are decremented in a taken branch, stopping at a maximum value, and are decremented at a non-taken branch, stopping a minimum value. Consequently, a counter value summarizes the dominant outcomes of recent branch execution. So, as sometimes after the prediction has been made, the actual branch outcome is evaluated. Dynamic branch history information can then be updated. It could also be updated speculative at the time the prediction was made. If the prediction was incorrect, instruction fetching must be redirected to the correct path. Furthermore, if instructions were processed speculative based on a prediction, they can be purged and the result must be nullified. The process of speculative executing the instruction is described in more detail later. Computing branch target. To compute the branching target usually requires an integer addition, and most architectures branch target at least 4 commonly used branches are relative to the program counter and use an offset value held in an instruction. This eliminates the need for read registers. However, the addition of the offset and the program counter is still required. Furthermore, there may still be some branches that do need register. Furthermore, there may still be some branches that do need register content to compute branch targets. Finding the target address can be sped up by having a branch target buffer that holds the target address that was used for last time the branch was executed. An example is the branch target address cache used in a power piece. So transferring the control. When there is a taken or a predicted taken branch, there is often a less clock cycle delay in recognizing the branch, modifying the program counter and fetching instructions from a target address. This delay can result in a pipeline bubbles unless some steps are taken. Perhaps the most common solution is to use the instruction buffer with its stockpiled instruction to mask the delay. More complex buffers may contain instructions from the both taken or the not taken the paths of the branch. Some of the earlier RISC instruction sets used to delay branches. That is, the branch did not take effect until the instruction after the branch. So with this method, the fetch of target instruction could be overlapped with the execution of instruction following the branch. However, in more recent processor implementation, delayed branches are considered to be complication because they make certain assumptions about pipeline structures may no longer hold in advanced superscalar implementation. Section 3.2 Instruction decoding and renaming and dispatching. During this phase, instructions are removed from the instruction fetch buffer, examine and control and data dependencies. Linkages are set up for the remaining pipeline phases. This phase included the detection of the true data dependencies due to the RAW hazard, and a resolution of other register hazards, for example WAW and WAR hazards caused by register reuse. Typically, this phase also distributes and dispatches instructions to buffers associated with the hardware functional unit for later issuing and execution. This phase works closely with the following issue stage, as will become apparent in the next section. The job of the decode phase is to set up one or more execution tuples for each instruction. An execution tuple is an ordered list containing 1. An operation to be executed, 2. The identity of the storage element where the input operand reside or will eventually reside, and 3. Location where the instruction's result must be placed. And the static program, the storage element are architecture storage element, namely the architected or logical and registers and main memory locations. To overcome the WA, WAR, and WAW hazard and increased parallelism during the dynamic execution. However, there are often physical storage elements that may differ from the logical storage element. So recall that a logical storage element can be viewed simply as a device to help describe what must be done. During parallel execution, there may be multiple data values stored on multiple physical storage elements, with all the values associated with the logical storage element. However, each of the values correspond to a different point in time during a purely sequential execution process. When an instruction creates a value for a logical register, the physical location of the value is given a name known as the hardware, and subsequent instructions which use the value as an input are provided with the name of physical storage location. This is accomplished in the decode, rename, dispatch phase in see figure 4 by the replacing the logical register name and instruction execution tuple, that is a register designator, and within the new name of the physical storage location. The register is therefore said to be renamed. There are two register remaining methods in common usage. In the first, there is a physical register larger than the logical register file. A mapping table is used to associate a physical register with the current value of the logical register. Instructions are decoded and register renaming is performed in sequential program order. When an instruction is decoded, its logical result register destination is assigned a physical register from a free list. That is, a physical registers that currently have a logical value assigned to them, and a mapping table is adjusted to reflect a new logical to physical mapping to the register. And the process of physical register is removed from the free list. Also, as part of the rename operation, the instruction sources register designators are used to look up their current physical register names in the mapping table. These are locations from which their source operand values will be read. The instructions dispatch is temporarily halted if the free list is empty. Figure 5 is a simple example of physical register renaming, the instruction being considered in the first add R3, R34 instruction. In figure 1, the logical architecture register are denoted with a lowercase letter, and the physical register are used uppercase. And the before side of the figure, the mapping table shows the register 3 maps to the physical register large R1, and the first available physical register in the first list in the R2 during R2. So during the renaming, the add instructions source register R3 is replaced with a large R1, and a physical register where a value will be placed by the preceding instructions. The destination register R3 is renamed to the first free physical register, R2, and this register is placed in the mapping table. And the substitution instruction that reads the value produced by the add will have its source register mapped to R2 so that it gets correct values. The example shown in figure 8, and to be discussed later, shows the renaming of all values assigned to register 3. Only the remaining method is the reclaiming of the physical register for free list after physical register has been read for the last time. It's no longer needed and can be placed back in the free list for use by other instructions. Depending on the specific implementation, this can require some more and less complicated hardware bookkeeping. One method is to associate a counter with each physical register, so the counter is incremented each time source register is named to the physical register, and it is decremented each time an instruction issues and actually reads a value from a register. The physical register is free whenever the count is 0, provided by the corresponding logical register has been subsequently renamed to another physical register. In practice, a method simpler than a counter method is to wait until the corresponding logical register has not only been renamed by the later instruction, but the later instructions has been received, each value has been committed. See section 3.5. At this point, an earlier version of the register is guaranteed to no longer be needed, including for precise state restoration in case of an interrupt. The second method for renaming uses a physical register file that is the same size as the logical register file, and the customary one-to-one relationship is maintained. In addition, there is a buffer with one entry per active instruction. That is, an instruction that is dispatched for execution, but which has not been committed. This buffer is typically referred to a reorder buffer because it is also used to maintain proper instruction ordering for precise interrupt. Figure 5 is example of a register renaming. A logical registers are shown in the lower case and a physical register are in the upper case. So figure 6 illustrates the reorder buffer. It is easiest to think of the FIFO storage implemented in the hardware as a circular buffer with the head and tail pointers. On instruction dispatched according to a sequential program order, they assign the entries at the tail of the reorder buffer. As the instructions completed the execution, their result values are inserted into their previously assigned entry. Wherever it happens to be the reorder buffer, and at the time an instruction reaches the head of the reorder buffer, if it has complete execution, each entry is removed from the buffer and its result value is placed in the register file. As an incomplete instruction blocks at the head of the reorder buffer until its value arrives. Of course, a Superscalar processor must be capable of putting a new entries into buffer and talking them more than one at a time. Nevertheless, adding and removing the new entries will follow the FIFO spline. A logical register value may reside either in a physical register file and maybe in a reorder buffer. When an instruction is decoded, its result value is first assigned to a physical entry in the reorder buffer, and a mapping table entry is set up accordingly. That is, a table indicates the result value can be found in the specific reorder buffer entry correspond to the instruction that produces it. An instruction source register designators are used to access the mapping table. The table either indicates that the corresponding register has the required value or that it may be found in the reorder buffer. Finally, when the reorder buffer is full, instruction dispatch is temporarily halted. In figure 7, show that the renaming process to apply to the same add R3, 4 instruction as in figure 5. At the time the instructions is ready for dispatch, the bit before the half of the figure, the values for R1 as through the R2 is resided in the register file. However, the value of the R3 reside or it will reside in the reorder buffer entry 6 until the reorder buffer entry is committed and the value can be written into the register file. Consequently, as a part of the remaining process, the source register R3 is replaced with the reorder buffer entry 6, row 6. The add instructions is allocated reorder buffer entry at the tail, entry number 8, row 8. The reorder buffer, as the number is then recorded in the mapping table for instructions that use the result of the add. In summary, regardless of the method used, to register remaining eliminated artificial intelligence due to the W8W and WAR hazard, leaving only the true R8W register dependencies. Section R 3.3 Instruction Issuing and Parallel Execution. As we have just seen, each in a decoder renamed the dispatch phase that execution tuple OP code plus physical register storage location is found. Once execution tuples are created and buffered, the next step is determined which tuples can be issued for execution. Instruction issue is defined as the runtime execution for availability of the data and resources. This is an area of a processing pipeline which is at the heart of the many superscalar implementation as the area contained window of execution. Ideally, instruction is ready to execute as soon as its input orders are available. However, other constraints they may place in issues of instructions, most notably availability of a physical resource, such as execution units, interconnect and register file, or the auto buffer port. Other constraints are related to the organization of the buffer holding the execution tuples. Figure 8 is an example of one possible parallel execution schedule for an iteration of the working example. Figure 1. This schedule assumes that the hardware source consists of two integer units, one path to the memory, and one branch unit. The vertical direction corresponds to timestamps, and the horizontal direction corresponds to the operations executed in the time step. In this schedule, we predicted the branch PLE was not going to take an NR to speculatively executing instructions from a predicted path. For illustrative purpose, we show only the rename the values for R3. In an actual implementation, the other registers would be renamed as well. Each of the different values assigned to R3 is bound to a different physical register, large R1, 2, 3, 4. The following paragraphs briefly describe a number of ways of organizing instructions issue buffers. In order to increase in complexity, some of the basic organization are illustrated in Figure 9. A single queue method. If there is a single queue and no out-of-order issuing, then register name is not required and operand availability can be managed via simple reservation bits assigned to each register. A register is reserved when an instruction notifying the register issue. The reservation is cleared when an instruction complete. An instruction may issue subject to the physical resource availability if there is no reservation on each operand. Multi-queue method. With multi-queues, instructions issue from each queue in order, but the queues may issue out of order with respect to one another. The individual queues are organized according to instruction type, and for example, there may be a floating point instruction queue, an integer instruction queue, and a load store instruction queue. Here, the renaming may be used in restricted form. For example, only registers loaded from a memory may be renamed. This allows the load and store queues from the sleeve ahead of other instruction queues, fetching memory data in advance of when it is needed. Some earlier Superscalar implementation used this method. The reservation stations. With reservation stations in Figure 10, which were first proposed as part of Tomasulo algorithms, instructions may issue out of order. There is no restricted FIFO ordering. Consequently, all of the reservation stations simultaneously monitor their source operand for data availability. The traditional way of doing this is to hold the data in the reservation station. When an instruction is dispatched to the observation station, an order, the already available operand values are read from the register file and placed in the reservation station. then reservation station logic compared to our operand designator of available data with the result designators of the completed instructions. When there is a match, the result is pulled into the matching reservation station. When all the operands are ready in reservation station, the instruction may issue subject to hardware sources availability. Reservations may be partitioned according to instruction type to register data paths, or may be pulled into a single large block. And finally, some recent reservation station implementation do not hold the actual source data, but instead hold pointers to where the data can be found. For example, the register file or reorder buffer entry. 3.4. The handling memory operations. Memory operations need special treatment in a superscalar processor. In most modern RISC instruction sets, only explicitly load and load store instructions access memory, and we shall use these instructions in our discussion memory operation. Although the concepts are easily applied to register storage and storage instruction sets. To reduce the latency of the memory operation, memory hierarchies are used. The expectation is that most data requests will be serviced by data cache memories residing at lower levels of the hierarchy. Virtually all processors today contain a data cache, and it is rapidly becoming the commonplace to have multiple levels of the data caching. For example, a small fast cache as a primary level of the somewhat slower but larger secondary cache. The most microprocessor integrate the primary cache on the same chip as the processor. Notable exceptions are some of processors developed by HP and the high-end IBM Power series. Unlike ALU instructions, for which it is possible to identify during the decode phase the register operand that will be accessed. It is not possible to identify the memory location that will be accessed by the load and store instructions until after the issue phase. The determination of the memory location that will be accessed requires address calculation, usually an integer addition. According to load and store instructions issued to an executed phase where the address calculation is performed. After address calculation, the address translation may be required to generate a physical address. A cache of translated descriptors of recently accessed pages, the transleucoside buffer (TLB), is used to speed up this address translation process. Once a valid memory address has been obtained, the load of a stored operation can be submitted to memory. It should be noted that although this suggests address translation memory access are done in series. In many superscalar implementations, these two operations are overlapped. The initial cache access is done in parallel with the address translation. Translation address is then used to compare the cache tag and determine if there was a hit. As operations carried out on registers, it is desired to have the correction of memory operations executed in as little time as possible. This means reducing the latency of the memory operations executing multiple memory operations at the same time. That is, overlapping execution of memory operations. Overlapping the execution of the memory operation with the non-memory operations and possibly allowing the memory operation to execute out of order. However, because there are many more memory locations than the registers, then because memory is indirectly addressed through the register, it is not practical to use the solution described in previous sections to allow the memory operation to be overlapped and proceed out of order. Rather than have name tables with information for each memory cache, as we did in the case of registers, the general approach is to keep information only for the currently active subset of the mandatory memory locations. That is, memory with the currently pending memory operations, and search this subset associatively when memory needs to be accessed. Some superscalar processors only allow the single memory operations per cycle, but this is rapidly become the performance bottleneck. To allow multiple memory requests to be serviced simultaneously, the memory hierarchy has to be multiported. It is usually sufficient to multiply only the lowest level of the memory hierarchy, namely the primary caches, since the many requests do not precede the upper level of the hierarchy. Furthermore, transfer from the higher level to the primary cache are in the form of lines containing the multiple consecutive words of data. The multiporting can be achieved by having multiported storage cells containing the by having a multiple banks of the memory, or by making the multiple series requests during the same cycle. To allow the memory operation to be overlapped with the other operation, both memory and non-memory, so the memory hierarchy must be non-blocking. That is, the memory request misses data cache. Other processing operations, including the further memory request, should be allowed to proceed. The key to the allowing memory operations to be overlapped or to proceed out of order is to ensure the data headers are properly reserved and the sequential execution semantic are preserved. Store address buffers and the simply store buffers are used to make sure that operations submitted to the memory hierarchy do not violate hazard conditions. A store buffer contains the addresses of pending or store operations. Before an operation, either a load or store is issued to the memory. The store buffer is checked to see if there is a pending store to the same address. The figure 11 illustrates a simple method for implementing hazard detection logic. Once the operation has been submitted to the memory hierarchy, the operation may hit or miss the data cache. In the case of the miss, the line containing the accessed location of has to be fetched into a cache. Further accesses the missing line must be made to wait other accesses may proceed. Mishandling status register MHSR are used to track the status of outstanding cache misses and allows the multiple requests to the memory hierarchy to be overlapped. 3.5 Committing the status. The final phase of the lifetime of the instruction is commit or the retire phase, where the effect of the instructions are allowed to modify the logical process state. The purpose of this phase is to implement the appearance of of a sequential execution model, even though the actual execution is very likely non-sequential, due to the speculative execution and out-of-order completion of instructions. The action necessary in this phase depends on the techniques used to recover a precise state. There are two main techniques used to recover a precise state, both of which require the maintenance of the two types of state. The state that is being updated as the operation executes, and other state that is required for recovery. In the first technique, the state of the machine at a certain point is saved and checkpointed in either a history buffer or a checkpoint. Instruction updates the state of the machine as they execute, and when a precise state is needed, it is recovered from the history buffer. In this case, all that has to be done in the commit phase is to get rid of history state that is no longer required. The second technique is to separate the state of the machine into two, the implemented physical state and a logical architectural state. The physical state is updated immediately as the operation complete. The architectural state of the machine is updated in sequential program order as the speculative status of the operation is cleared. With this technique, the speculative state is maintained in a reorder number buffer. To commit an instruction at regions has to be removed from the reorder buffer into the architectural register file and to memory in case of the store. And the space is freed up in a real buffer. Also, during the commit phase of a store instruction, a signal is sent to the store buffer and the store data is written to the memory. Only part of each reorder buffer entry is shown in figure 6. And because we were illustrating the renaming process, only the designator of the reserve register is shown. Also in reorder buffer entry is a place for the data value after it's been computed. But before it's committed, but before it is committed. And there is typical place to hold the program counter values of instructions and any interrupt to condition that might also result in instruction execution. These are used to uniform the commit logic, and when then an interrupt should be initiated at the program counter value that should be enters as part of the precise interrupt status. Thus far, we have discussed the reorder buffer method that is used to implementations which use the reorder buffer method of register renaming, as illustrated in Figure 6. However, the reorder buffer is also used for the other style of renaming, where the physical registers contains all the renamed values as in Figure 5. With the physical register method, the reorder buffer does not have to hold values prior to being committed, rather than they can written directly into the physical register file. However, the order buffer does hold control and interrupt information. When an instruction is committed, the control information is used to move the physical registers to the free list. If there is interrupted, the control information used to adjust the logical to physical mapping table so that the mapping reflected correct precise state. Although the checkpoint and history buffer method has been used for some superscalar processor, the reorder buffer technique is far the more popular technique because, in addition to the providing a precise state, the reorder buffer method also helps implementing the register renaming functions. Section 3.6 The role of software. Though a major selling point of the Superscalar processor is to speed up the execution of the existing program binaries, their performance can be enhanced if new unmatched binaries can be created. Software can assist by creating a binary so that the instruction fetching process, the instruction issuing the execution process can be made more efficient. This can be done the following two ways. One, increasing the likelihood that the group of instructions that being considered for issue can be issued simultaneously, and decreasing the likelihood that an instruction has to wait for a leisure of previous instructions when it is being considered for execution. Both these techniques can be accomplished by the scheduling instructions statically, by arranging the instructions so that a group of instructions in the static program matches the parallel execution constraint of the underlying superscalar processor. The first objective can be achieved. The parallel execution constraint needs to be considered include dependency relationships between the instructions and the resources available in the microarchitecture. For example, to achieve the parallel issue of the 4 consecutive instructions, the microarchitecture might require all four of them to be independent. To achieve the second objective, an instruction which produces a value for another instruction can be placed in the static code so that the fetch it and execute far in advance of the consumer instructions. The software support for a high-performance processor is a vast subject, one that cannot be covered in many detail in this paper. A good discussion of the software topics appear in the article, and this issue written by the One Mei Hu. 4. Chapter 4. 3 Superscalar microprocessors. In this section, we discuss the current superscalar microprocessor in the light of the above framework. The three were chosen to cover the spectrum of the superscalar implementations as much as possible. They are missing R10000 and which fit the physical typical framework described above, and DC Alpha 21164 which arrived for greater simplicity, and the AMD-K5, which implemented more complex and older instruction set than the other two in the Intel x86. Section 4.1 myths are 111. The myths are 10,000 does extensive dynamic scheduling is very similar to our typical superscalar processor described above. In fact, Figure 4 is modeled after the R10000 design. The R10000 design fetched 4 instructions at a time from the instruction cache. These instructions may have been pre-decoded when they were input into the cache. The pre-decoder generated 4 additional bits for instructions which help determine the instruction type immediately after the instructions are fetched from the cache. After being fetched, branch instructions are predicted. The prediction table is contained within the instruction catch mechanism. The instruction catch holds 512 lines of there are 512 entries in the predictable table. Each table in the prediction table holds a 2-bit counter value that encodes the history information used to make the prediction. So when a branch is predicted to be taken, it takes a cycle to redirect to instruction fetching. During that cycle, sequential instructions, that is those on a non-taken path, are fetched and placed in the resume cache as a hedge against incorrect prediction. The resume cache has a space for 4 blocks of instructions. For 4 branch instructions can be handled at any given time. Following instruction fetch, instructions are decoded, their register operands are renamed, and they are dispatched to the appropriate instruction queue. The procedure which mentioned earlier simplified this process. All register designators are renamed using physical register files twice the size of logical files, 64 physical values that are logical. The destination register is assigned to an unused physical register from the free list, and the map is updated to reflect a new logical to physical mapping. The operand register are given to the correct designators by reading the map. Then, up to 4 instructions at a time are dispatched into one of 3 instruction queues: memory, integer, and floating point. That is, the R10000 uses the form of queued instruction issue as in Figure 9c. Other than the total of the most 4, there are no restrictions on the number of instructions that may be placed in any of the queues. The queues are each of the 16 entries deep, and only a few queue can block dispatch. At the time of the dispatch, a reservation bit for each physical register is to set to busy. Instructions in the register are integer and floating point instructions. Queues do not issue in a true FIFO spline. Hence, the term queue is a little misleading, so that the queue entries act like a reservation station. However, they do not have a value field and a more valid bit as in Figure 10. Instead of value field, the reservation stations hold the physical register designators which serve as a pointer to the data. Each instruction in the queue monitors the global register reservation bits for each source operand. When the reservation bits or becomes not busy, the instruction source operands are ready and are subject to availability of the functional unit. That instruction is free to issue. There are 5 functional units: an address adder, 2 register, 2 integer ALUs, and a floating point multiplier divider scale router, and a floating pointer adder. The 2 integer ALUs are not identical. Both are capable of the basic add and subtract logical operation, but only one can do shift, and the other can do the integer multiplication and addition. So, as a general policy, an effort to be made to process the ordered instruction first when more than one instruction has a ready operand and is destined for the same functional unit. However, this policy does not result in a strict priority systems in order to simplify the arbitration logic, the memory queues, and however does prioritize the instructions according to age, which makes the address hazard detection simpler. The 10,000 support an on-chip primary data cache, 32-bit two-way set associated with 32-bit byte lines, and an off-chip secondary cache. The primary cache blocks only on the second miss. The R10,000 uses real buffer mechanism to maintaining a precise state at a time of execution of the condition. The instructions are committed to the original program sequence up to 4 at a time. When an instruction is committed, it frees up the old physical copy of the logical register and modified. The new physical copy, which may have been written many cycles before, becomes the new architecturally precise version. Exception conditions for non-committed instructions are held in a reorder buffer. When an instruction with the exception is ready to become the committed, uninterrupted will occur. So information in the reorder buffer is the instructions following the interrupting one are used to adjust the logical physical register mapping so that the logical state is consistent with the interrupting the instructions. When a branch is predicted, a processor take a snapshot of the register mapping table, then the branch is subsequently found to be mispredicted. A register mapping can be quickly restored. There is space to allow the snapshots of up to the 4 predicted branches at any given time. Furthermore, by using the resume cache, instruction processing can often begin immediately. Section 4.2, the alpha 21 is 164. The alpha 21-164 figure 12 is an example of the simple superscalar processor that foregoes the advantage of dynamic instruction scheduling in favor of the high clock rate. Instructions are fetched from an 8 kilobyte instructions cache for at a time, and these instructions are placed in a one instructions buffer, each capable of holding 4 instructions. Instructions are issued to the buffer in program order, and a buffer must be completely emptied before the next buffer can be used. These restricted instruction issues are rated somewhat, but it greatly simplifies the necessary control logic. And branches are predicted using the table is associated with the instruction cache. There is a branch history entry for each instruction in the cache. Each entry is 2-bit counters. There can be only one predicted and yet unreserved branch is a machine at a time. Instruction issue is stored if another branch is encountered before the previously predicted branch has been reserved. The following instruction fetch and decode instructions are expected, arranged according to type that is functional until they will use. Thus, then the provided operand data is ready and registers are available for bypassing. The instructions are issued to the units and begin execution. During this entire process, instructions are not allowed to pass to another. The 21-1 is therefore an example of the single queues method shown in figure 9a. There are 4 functional units to integer ALUs, a floating point adder and a floating pointer multiplier. The integer ALUs are not identical. Only one can perform a shift and integer multiplies. The other is the only one that can evaluate branches. The 21-164 has 2 levels of cache memory on the chip. There are a pair of small, fast primary caches of 8 kilobytes each for one for instructions, one for data. The secondary cache shared by instructions and data is 69 bytes as the 3 ways that associated. The small directly mapped primary caches allow the single cycle cache accesses at a very high clock rate. The primary cache can sustain a number of those outstanding misses. There is a 6-entry miss address file, MAF, that contains the address, the target register for a load that misses. The address is to the same line as another address is the MAF, and the two merged into the same entry. And the MAF can hold many more than 6 substandard cache misses. In theory, it's up to 21. To provide a sequential state of at the time of the interrupt, at the 164 does not issue out of order and keeps instructions in the sequence that they flow down the pipeline. The final pipeline stage updates the register file in the original program sequence. There are bypasses along with the pipeline so that can be used before it is committed to the register file. This is a simple form of the old buffer with bypasses. The pipeline itself found the reorder buffer, and the order is maintained so reorder overstated what is actually done. Floating point instructions are allowed to update their files out of order, and as a result, not allowing the point exception, resulting in a precise architectural status. The section 4.3, the AMD-K5. In contrast of other microprocessors discussed in this section, the AMD-K5 Figure 13 implement an instruction set was not originally designed for a path pipeline implementation. It's an example of a complex instruction set, the Intel x86. The Intel 86 instruction set uses a variable length instruction. This means, among the other things, on one instruction must be decoded, and each length established before the beginning of the next can be found. Consequently, instructions are sequentially pre-decoded as they are placed in the instruction cache. There are 5 pre-decoded bits per instruction byte. These bits indicate the information such as whether the byte is in the beginning or the end of an instruction and identify the bytes holding copy codes and operand. Instructions are often fetched from the instruction cache at a rate of up to 60 bytes per cycle. These instruction bytes are placed into a 16-element byte queue where they wait for dispatch. As in the other microprocessors described in this section, the K5 integrates branch prediction logic with the instruction cache. There is one prediction entry per cache line. An instruction bit reflects the direction taken by the previous execution of a branch. The execution entry also contains a pointer to a target instruction, and this information indicates where the instruction cache the target can be found. This reduces the delay for caching predicted target instruction. Due to the complexity of an instruction set, 2 values of the consumed are decoding. At the first stage, the instruction bytes are read from the byte queue and are converted in simple RISC-like OP operations, called by ROPs by the AMD. Up to 4 ROPs are formed at a time. Often the conversion requires a small number of ROPs for x86 instruction. In this case, the hardware does a single cycle conversion. More complex x86 instructions are converted into a sequence of ROPs via sequential lookup from ROM. In this case, the ROPs are essentially from a microcoder. Up to 4 ROPs per cycle are generated from ROM. After conversion of the ROPs, most of processors are focused on their execution as individual operations, largely ignore the original x86 instructions from which they were generated. Following the first decode cycle, instruction read operand data. If available, dispatches the functional unit observation status up to 5 ROPs per cycle, corresponding to the up to 4 x86 instructions. Data can be in the register file or can be held in the reorder buffer. When available, the status read and sent with the instruction to the functional unit reservation station. If the operand has been not computed, the instruction will wait for in a reservation station. There are 6 functional units, 2 integer ALUs, and 1 floating point, 2 load store units, and a branch unit. One of the register ALU capable of shifting of the other can perform the integer divide. Although they are shown in a figure single block in figure 13, the reservation stations are partitions among the function unit. Except FPU, each of the units had 2 reservation stations. FPU has only one. Based on available data, ROPs are issued from the reservation stations on their associated functional unit. There are enough register supports and data paths to support up to 4 such ROP issues per cycle. There is an 8 kilobyte data cache which has 4 banks. Dual load and stores are allowed, provided they are to the different banks. One exception is if both latent references are to the same line, in which case they can both be served together. A 16 re-entry reorder buffer is used to maintain the precise process state when there is inception. The K5 reorder buffer holds the result data until it is ready to replace the register file. There are bypasses from the buffer, and associated lookup is required to find the data after complete, but pending the register write. There is a base class reorder buffer method of the renaming we described earlier. The order buffer is also used to recover from the incorrect branch prediction. 5. Conclusion. What comes next? Both performance and compatibility have driven the development of the Superscalar processors. They implement a sequential execution model, although the actual execution of a program is far from sequential. After being patched, a sequential instruction stream is torn apart with only true dependencies holding instructions together. Instructions are executed in parallel with a minimum of the constraint. Meanwhile, enough information concerning the original sequential order is retained so that the instruction stream can conceptually be squeezed back together again should there be need for a precise interrupting. A number of studies have been done to determine the performance of Superscalar method, for example. 4. Because the hardware and software assumptions and benchmarks vary widely, so do the potential speedups, ranging from close to 1 for some program hardware combinations to many hundreds for others. In any event, it is clear that there is something to be gained in every microprocessor manufacturer has embraced the Superscalar method for high-end products. So the wider Superscalar implementation have become a staple, just like a pipelining. There is some consensus that returns are likely diminished as more parallel hardware resources are introduced. There are a number of reasons for thinking this. We give two ways of the more important. First, there will be a limit to the instruction level parallelism that can be exposed and exploited by currently known the Superscalar method, even if the very aggressive method are used. Perhaps the most important of these results are conditional branches. The studies that compare the performance using the real branch prediction with a theoretically perfect branch prediction note to a significant performance decline where the real prediction is used. Second, Superscalar implementation grew in complexity as the number of simultaneously issued instructions increases, data path complexity, numbers of functional units, register and cache ports, for example, grows for obvious reasons. However, control complexity, also known, grows because of the cross-checks that must be between the all instructions being simultaneously dispatched and/or issued. This represents the quarterly growth in control complexity, which sooner or later will affect the clock period that can be maintained. In addition, there are some important system level issues that might ultimately limit performance. One of the more importance is the widening gap between the processor's main memory performance. While the memories have gotten larger in each generation, they have gotten much faster. Processor speed, on the other hand, have improved markedly. A number of solutions are considered, ranging from the more sophisticated data cache design, better cache pre-patch method, more developed memory hierarchies, and memory chips design that are more effective at providing data. This issue affected all the purpose method for the increased instruction level parallelism, not just the Superscalar implementation. In the absence of the radical new Superscalar method, many believe in it way Superscalar more or less is a practical limit. This is a point that will be latched to within the next couple of generations of the processors. Where do we go from the point? One school of the thought believes that a very large instruction word VLIW model will become the paradigm of choice. The VLIW model is derived from the sequential execution model, control the sequence from the instruction to instruction, just like a sequential model discussed in this paper. However, each instruction in the VLIW is a collection of several independent operations which can all executed in a parallel. This compiler is responsible for generating a parallel execution schedule and representing execution schedules as a collection of VLIW instructions. If the underlying hardware source necessitated the different execution schedule, a different program binary must be generated for optimal performance. VLIW components claim several advantages of their approach, and we will summarize two of the more important. First, with the software being responsible for analyzing the dependencies and decreasing the execution schedule. The size of the instruction window that can be examined for parallel is much larger than what superscalar processor can do in hardware. Accordingly, a VLIW processor can expose more parallelism. Since the control logic in a VLIW processor does not have to have any dependence checking, the entire parallel execution schedule is orchestrated by the software. VLIW hardware can be much simpler to implement, and therefore may allow the faster clock than a superscalar hardware. VLIW proponents have other arguments to favor their approach, and VLIW opponents have the counter argument in each case. The argument typically centers around the actual effect of the scalar logic complexity, and will have the performance and ability to VLIWs compile time analysis, match dynamic scheduling using the runtime information. With announced plans of the Intel and Hewlett-Packard and with other companies seriously looking at the VLIW architectures, the battle lines have been drawn and the outcome may be known in a very few years. Other schools of the thought strive to get away from the single flow of the control mindset prevalent in the sequential execution model and the superscalar implementation of the model, rather than sequence through the program instruction by instruction in an attempt to create a dynamic instruction sequence from the static representation. More parallel forms of sequence may be used. In 39, it is shown the online multiple control flows provided a potential of the substantial performance gain, and that is multiple program counters can be used for fetching instructions. Then the effective windows of execution from which independent instruction can be chosen for a parallel execution can be much wider. One such method is variation of a time-tested multiprocessing method. Some superscalar, meaning supercomputer vendors, have already implemented an approach for automatic parallelization of the high-level language program, which, with the chip resources being sufficient to allow multiprocess to be integrated on a chip. Multiprocessing, once domain of the supercomputers and mainframes, is being considered for high-end microprocessor design. After multiprocessing is exploit instruction level parallelism at a very small grain size that is designed. If multiprocessing is to exploit instruction level parallelism at a very small grain size that implied by the instruction level, suitable support has to be provided to keep the interprocessor synchronization and communication overhead extremely low. As a traditional multiprocessing, single-chip multiprocessors will require an enormous amount of compiler support to create a parallel version of the program statically. Looking even far ahead, more than analytical approaches support multiple flows of controllers being studied. In these approaches, individual processing units are more highly integrated than a traditional multiprocessor and a flow control mechanism built in the hardware as well. By providing a mechanism to support speculative execution, such method allows a parallel execution of programs can to be analyzed and parallelized statistically. Microprocessors design have successfully passed the simple pipeline to simple superscalar implementation, and fully developed superscalar processors or in little more than a decade. Within the benefit of hindsight, which step seems to be a logical progression from the previous one. Each step tapped new sources of the instruction level parallelism. Today, researchers and architects are facing new challenges. The next logical step is not clear, and the search for new innovative approaches to instruction level parallelism promises to make the next decade as exciting as the previous one. Today I read this long paper, The Microarchitecture of Superscalar Processors. Thank you for your time. See you next time.